So here's another example which is relevant to the display of tidal currents. Tidal currents are something that repeat all the time. They have a specific period. It's an oscillation that repeats. Like semi-diurnal tides, they repeat on time scales of a little bit longer than 12 hours. Okay, and you learn all about tides later on, but it's something that repeats. You have something which is a cyclic event. So if something repeats, you can use something which is called a hodograph to display current. Okay, and this is known as a tidal ellipse. So what's shown here in the top graph is one example where you actually show your horizontal flow vector at a specific time. Okay, and this is after 1 hour. So you actually indicate what time it is. This one is your start time, if you like. And you actually draw the arrow after one hour. And after 2 hours, you draw another arrow. And after 3 hours, and so on. And then you do it over time. And you get over, in this example here, it's a full 24 hours. So these ones are diurnal tides. Okay, they have a different period than the semi-diurnal tides. But you get a representation of the flows that over a cycle that repeats and repeats and repeats. Okay? And the hodograph itself often, or the tidal ellipse itself, is actually often even shown without the arrows. So you only see the dots around the endpoints of these arrows. And here is another example. So at the bottom here is another example. You can also convert these flow vectors into displacement diagrams, so-called progressive vector diagrams. And it uses the conversion that distance is speed times time. But I come to that on one of the next graph. But these things here are called tidal ellipses. Okay, and I show you one example. This is one example for Monterey Bay, one particular tidal component. The details don't matter, but for each of the location, it actually shows a tidal ellipse. Okay, and just focusing on some of the details. For example, there are regions where you see only a line, means that the flow only goes into one direction at some time, a point in time, and then into the opposite. So the flow moves northwestward and then southeastward. Okay, and it changes all the time. It's an oscillation. It goes back and forth. So you can even imagine that if you have a particle in this flow, it goes into one direction and then back, and so on. And in other directions, you have more a circle pathway, which means that the direction changes all the time. Okay, it's a systematic change of direction. So at one time the flow is to the north, then to the east, then to the south, and then to the west. So you only see the endpoint of your hodographs here. And if you chuck a float into that tidal current, it would also undergo a circular pathway horizontally. Okay? So this one gives you, this is a method by which you can show the tidal currents in a region. And indeed, the size of these axes of the ellipse tell you how strong the tidal current is. You can see here in this diagram, there's a little sketch here. It tells you if you have a size which is called the major axis here, corresponds to 5 centimeters. So if you have that length in your tidal ellipse, okay, you can convert it to speed. Okay, this is what we call a tidal ellipse. It's a method very useful for the representation of tides which repeat all the time.